Swayam Prabha. Digital India. Educated India.
Hello everyone, today is the fourth day of this week and what we'll do today is we will revisit the example problem we had discussed on the second day of this week, that is heat conduction problem. That time we tried to get a solution with three-noded triangular element. We could not apply quadrilateral element that time because in order to apply quadrilateral element, we need to know the concept of isoparametric formulation. In the last class, we had discussed isoparametric formulation. So now we are in a position to take that example once again and apply quadrilateral element and then see what happens to the solution if we change the element. So I will take you directly to the problem. This was the problem. Now this is the domain and then primary variables, secondary variables, all are specified. So first step is to discretize the domain. So this is the domain, we need to discretize it. Now let us discretize it with one quadrilateral element. Again, the one quadrilateral element we are using, two reasons. One reason is eventually we will compare the result with the results of the triangular element, what we already know. Now, first reason is we need to have a less number of quadrilaterals so that our number of equations are less, so that we can get the solution in the class itself. And another important reason is we try to, when we compare, we should be on the same basis. So in the second lecture, when we tried to get a solution with triangular element, the total number of nodes, the global nodes were 4. We had 2 elements, but the number of nodes were 4. So here also we want to keep the number of nodes 4, right? So that the comparison will be relatively fair. Now, so this is the one quadrilateral element. This is element number 1 and these are our node number 1, 2, 3, 4. This node number is local node, element level node number and global node number will be same because we have just one element. And you will see that assembling we don't have to do because element equation will give you the global equation. Now, so first step, so this is the discretization, which is the first step, and the next step is to write the element equation. So element equation, let us summarize the equation. This is the element equation. And K is the coefficient matrix, and then we have source term and the boundary flux term, and the coefficient matrix is obtained by this when B depends on the shape function and its derivative of the shape function. F term is given by this, and then Q, the boundary flux term, is this, right? Now, so we have B is written. So B already we know, this is how the B is written. So this we know. So and C is this, in this case it is constant. So before we write all this, when we say element level equation, means we need to compute this, we need to compute this, we need to compute this. But before we do so, let us just quickly review the important concept of isoparametric formulation. We already had a discussion in detail in the last class, but just to have a completeness in the entire discussion today. So this is the isoparametric formulation. We have a physical element which is the physical domain in XY coordinate system where actual structure, the actual domain exists. Okay. And then we have a parent element which is also called the parametric element, parametric domain. and xi eta are the natural coordinates. Now the parametric element are always written in this. This is the domain is of the parametric element is like this. Then we define a map. The concept is the shape function that we use to approximate the variable, and the shape function, the same shape function we use to approximate the geometry as well. So these shape functions phi, this is a function of xi eta. It is constructed on the xi eta coordinate, and then any global xy in the physical domain, any point in the physical domain is mapped to the global domain, to the local domain like this. Okay, where x, c, I are the coordinates of these points 1, 2, 3, 4. So we know this. Now this will directly give us how the derivatives with respect to different coordinate systems are related to each other, right? Where j is the Jacobian, and so j Jacobian is written like this. These phi are the function of xi and eta. It is constructed on the parametric domain, parent element. So we already know for a 4-noded quadrilateral, these are the shape function, right? So now what we'll do is we will use this shape function to get the Jacobian, and once we have the Jacobian, through this transformation, we will write the derivative with respect to x and y in terms of derivative with respect to xi and eta. So this is, we know. Another thing, let us quickly review the integration over quadrilateral domain. We had a discussion on the numerical integration through Gauss quadrature technique in the last week, and we had seen that there are different rules we can use to integrate depending on the order of the polynomial we want to integrate, and this is how the integration done. We need to integrate any function over domain omega e, which is a physical domain, and this integration is now mapped to the integration over parametric domain, and the extent of the parametric domain is defined like this, and then this is written in summation form. The idea is we get some integration points and evaluate the function at the integration point, multiply by their weights and take the sum, will give you the integration, and NGP is the rule of the integration. For this, it is 1-point integration. Our integration point is 1. It is 2-point integration. NGP is 2, means we have 2 points in xi direction, we have 2 points in eta direction, 2 points. The total number of points are 4. Similarly, Gauss in 3-point rule means in xi direction you have 3 points, and in eta direction 3 points, and total number of integration points are 3. So we know this. This is how this integration can be done. Now we have to do this integration here because we will see this eventually. This coefficient matrix involves now the inverse of Jacobian and the Jacobian determinant of Jacobian. So we have a nonlinear equation that needs to be integrated. So we will use using Gauss quadrature technique. So let us write the element equation. Start with the coefficient matrix. So this is the expression for the coefficient matrix we know, and this coefficient matrix can be written. This integration can be performed using Gauss quadrature technique like this. Now where b is now expressed, here b is written as a function of x and y, but here we need to write b as a function of xi and eta. So then this, if in a summation form, we can write this, right? So we will use 2-point Gauss quadrature technique. We will see the kind of the order of polynomial eventually we'll get in this 2-point rule will be sufficient. So so we know b is equal to this. That needs to be written. B is a function of x and y. This needs to be expressed as a function of xi and eta. So this involves derivative with respect to x and y, and derivative with respect to x and y is related to derivative with respect to xi and eta like this. This is the inverse of Jacobian, and this will give us this, right? So b with this in terms of xi and eta can be represented like this, and we already know these are the shape functions phi 1, phi 2, phi 3, phi 4 with respect to in terms of xi and eta coordinates. And if we do that, then we will see, if you substitute the del phi, del xi and del phi, del eta with this from this, we'll get an expression like this. So this will be the B written in terms of xi and eta. So now in this expression, we need to find out what is the inverse of Jacobian. Let's do that. So Jacobian is written like this. This is how the Jacobian is defined. We have seen this in the last class, right? Now, so these are the shape functions. Substitute this shape function in this matrix, Jacobian matrix. If you do that, our Jacobian will be so this Jacobian will be like this, and then if we substitute this in this expression, Jacobian will be this, where xc, these are the points of the coordinates of the points of the nodal points in physical domain, in the physical with respect to x and xy coordinate system. Okay, so this is the Jacobian now we have. So let us, this is the general expression of Jacobian. Now let us write the values of this, substituting the values of x, y and so. So these are the coordinates we have. So these are the coordinates. So x, and in this expression we have seen that Jacobian is this. So substitute this coordinate in that. So we get Jacobian as this, and this eventually will give us this. So this is the Jacobian, right? So once we have this Jacobian, now let us get the inverse of this. Inverse determinant of Jacobian will be this, and inverse of Jacobian will be this. And this inverse is important because this is how these derivatives are transferred. Okay. Now, once we have this inverse of Jacobian, we already had seen that B is as a function of xi eta can be written like this. So if we substitute this, so we have an expression for B as this. Now this expression we do not have to evaluate. Now this is a now function of xi and eta. Entire B is represented as a function of xi and eta. Xi and eta means now this B. So once the B is written in terms of xi and eta, we can get the element of the coefficient matrix as a function of xi and eta, and then that element needs to be integrated over the entire domain, and that integration we can do using quadrature technique. So so we know that this is the coefficient matrix. So we'll use 2-point quadrature rule, and 2-point quadrature rule will give you if n-point quadrature rule can integrate a polynomial up to 2n minus 1, means here 2-point quadrature rule means we can integrate a cubic polynomial. So this is so we will use it now. So these are the, you can try increasing the number of Gauss point, increasing the quadrature rule, and then see what happens to the solution. That would be a very interesting exercise to do, and then see you get the same solution or a different solution. You can also try with 1-point Gauss quadrature rule, and then see the result. Okay. So now for 2-point quadrature rule, we know that these are the positions of there are 4 points, and these are the coordinates of these integration points. These coordinates are in parametric domain, and the corresponding weights are this. So now we need to evaluate this entire expression at these integration points multiplied by their weights, and then sum them. So, and of course that has to be multiplied by the determinant of Jacobian, and finally we have the k. So if we do that, we have a coefficient matrix like this. Okay. So individually you can that exercise we are not doing it here, because now we know what has to be done. If you can do that and then verify whether you are getting this matrix or not. As I said, you can check with 1-point quadrature rule. This is with 2-point quadrature rule. You can check with 1-point quadrature rule, and then we have 2-point quadrature rule, and also you can check with 3-point and 4-point quadrature rule, and then see what happens to this coefficient matrix. So this is the coefficient matrix we have now at the element level. Okay. Now next is the source term we have to find out. Source term is also very straightforward. This is to be integrated over this entire domain omega, and then f is constant in our case. So this f e we can take it out, and since now this is you can integrate using the same concept we can use to integrate the quadrature technique, and then these are the quadrature points just now we have discussed, and evaluate all these these quadrature points and then multiply the weight and then sum it, we get the result. So this is our FE. Now, so this is the source term. Then finally we have the boundary flux term. Now the boundary flux term is we know this is the expression. This is a boundary integral, and this has to be integrated. This has to be evaluated on the element boundary, which coincides with the natural boundary, where the natural boundary conditions are prescribed. So this essentially needs to be integrated over this line 1, 4, and we follow the same approach we had already discussed. What is the approach? We can do this is our element, and we can have a local system like S, and element number is, this is 1, 2, 3 and 4. So this is we are going anti-clockwise direction. That's why the direction of S will be this, and on this we have a constant Q. We have constant Qn, and Qn is constant, and then it needs to be integrated. And since it is constant, it will be equally distributed at node number 1 and node number 4. So our expression will be at node number 1 it will be minus 15, and node number 4 it will be minus 15. Okay. So this integration essentially needs to be done over this over this line, right? So we have all the term, coefficient matrix, boundary flux term and the source term at the element level. Ideally, next step is to assemble the element matrices, but now in this case just we have one equation. So this equation, element level equation, is essentially the global equation. So we have the global equation like this, and same thing, these are 1 or 2 or 3 are the sources, are the residues. Now next step is, once we have this global equation, next step is to impose the boundary condition. And what boundary conditions we have? We have at this point T1 is equal to 0, T2 is equal to 0, and T3 is equal to 0. And if we substitute that, impose the boundary condition, and final equations will be this. So see, these all will be 0, right? This will be 0. Only unknown we have is T4. So next is we partition this and get the condensed matrices, and then solve these condensed matrices to get the primary variable. And once we know the primary variable, we can use other condensed matrix to get the secondary variable. So here in this case, if we get the last equation, and it will give us T4 is equal to this minus 1, 4. So this is the solution we obtained using one quadrilateral element. Now recall this, we had, as I said, we had already solved it using constant strain triangle, 3-noded triangular element, and at that time our solution was this. But let us not take either of the solution, whether solution obtained from triangular element and solution obtained from the quadrilateral element. Whatever solution we have obtained so far, let us not take that solution for granted. We need to check. What next we will do is we will increase the number of element. We will do both the cases, triangular element and quadrilateral elements both. We will increase the number of elements and then see what happens to the solution and whether it converges or not, and in which case we'll get better convergence. So, but for that we need to have a small program, because that exercise cannot be done manually. So next class we'll write a small program, and then through that program we will do this exercise. Okay, so let us stop here today. See you in the next class.